I'm a security researcher at Assured Information Security. My interests include computation and language theory, no surprise, and various transmission media, so like radio. And in case you guys are wondering, I like long bounded walks on the beach. So as a little bit of an overview of what we're going to be talking about today, we're going to give a little history of what was the precedent for MoCA and what we're trying to accomplish with it. We're going to talk a little bit about how the experiment is formulated and some of the preliminary results we've seen so far, and try to draw some imparting takeaway message from this. And I can't stress this enough. I prefer to have an open forum, if possible, for having questions. So if you have one, just shoot one out there. That way we're all moving along on the same train. So the preceding effort, as Sergey was talking about, was called Crema. It was, and I'm sure he'll correct me if I'm wrong on this, but it was an effort to measure the effect of restricting computation on formal languages. So I believe they created a sub-Turing-complete programming language and measured how the effect of porting languages into that. So that begs the question, going so far, begs the question of, okay, so we know we can do this. We know its impact. How prevalent is being able to run code in sub-Turing-complete environments? So meaning, like, if we looked at a large code base, how much of that can be run sub-Turing-complete? So that's the goal of MoCA in a nutshell. We're trying to look at large data sets and, based on what we're seeing, classify certain code portions as either fully Turing-complete or sub-Turing-complete, or somewhere in between, we don't know. So I have to apologize for this. If you guys know this already, bear with me. But why do we care about whether or not something's Turing-complete? Well, Turing-complete code can accept arbitrary inputs. Inputs govern program execution behavior. Okay, sorry. And because of that, we can get ourselves into undesirable or untrustworthy states, so the land of weird machines in this case, so we don't enjoy that. However, on the contrast, sub-TC execution is restricted and well-defined behavior, and from that we can actually have determinate operation, and it can be proven safe from a LangSec perspective. Unfortunately, this can't be applied to all applications, so input handling has to be, take a user input, and so that's kind of at the discretion of the user and possibly a payload writer. So the whole point of this is to make a case for LangSec. We're not trying at this point to say it's possible to do LangSec here. We're trying to say that it's not only possible, it's almost stupid not to be writing code with LangSec in mind. So I think Dan Greer last year talked about the 5 stages of code of acceptance. We should be pushing for that 5th. We should actively be saying, why aren't we doing LangSec with our stuff? So for the actual code we're working with, we're using LLVM and Clang to do compilation and analysis. Linux kernel version 4. I don't remember the subunit that we're working with, but if you look at kernel.org, it's the latest stable release. And I should mention here that when I say we're working with the kernel, we're working with the micro version of, not the micro, but a tailored down version, so specifically for our computers, so the tiny configs. And Python version 2.7 for doing analysis of the output of LLVM. So you may be asking, why LLVM, why not GCC? LLVM has a little bit better extensibility, which is what we're really looking for here, because as you'll see, we're writing custom passes for a lot of the analysis, as well as doing some transformation passes, so we're modifying the intermediate representations of the code to make it a little more obvious to us as to whether or not something will be TC or sub-TC. And additionally, it also allows for a little higher degree of verbosity, which allows, again, for us to do better metrics on what we're working with. So now that we have, in theory, this output from compilation, what are we looking for? We're looking to care about things like input language, SLOC, so those guys of you who didn't spend time as a software engineer in a previous life, source lines of code. and minimum machine power classification. So at what least privileges, right? So what's the lowest power machine that we can run this with? But in this case, it's just sub TC and TC. That being said, this is obviously broaching on the halting problem. So that's what interns are for, manual analysis. But in all actuality, a lot of this is attempted to be done through our code base itself. So as I said, we're running transformation passes. What does that mean? It means the ability to look at code that may be somewhat ambiguous and take that code and work it around a little bit to display that it actually is either Turing complete or sub-Turing complete. And we'll show an example of that in a little bit. So when we talk about completeness, we think about loops. So for our cases, things like loops with very well-defined upper bounds for their induction variables easily terminate. I mean, and that being said, there are obviously, you might ask, what about things that modify the loop variables internally? It gets handled by a loop pass in LLVM already, so it's smart enough to do that. We have some things that are more ambiguous, and you'll see they're pretty prevalent. Recursion you also think of a lot of times when you talk about Turing completeness. And LLVM does have the ability to fully unwind some things if it knows that the thing can be completely unwound, rather. So we can count those as sub-Turing complete and default to say, like, we'll have to manually analyze it after. But in general, you don't really see recursion in the kernel. It's just not something they do. So it's not really an issue for us. So a completely contrived example of what we usually look at when we look at the intermediate representations of things. Basic silly loop, I less than 0, I plus plus. You can look on line 3 of that and see that there's a comparison operation between the induction variable I and 10, like static 10. So we know from that, great, this is perfect, it terminates. Let's classify this as a sub-Turing complete piece of code. But unfortunately, not many people write code like that. So what about something a little more complicated? And this is much more descriptive of what we actually see in the kernel, at least, is that we see some sort of buffer being defined, and we define the upper bound for a loop as one element that buffer. We see this a lot in drivers, a lot of times in the x86 folder of the kernel. And you'll see on the first example here on the top, the second line of this piece of code, you see this buffer, and it doesn't know what to do with this. So when we actually look at, when we ask LLVM, does this have an upper bound? It'll say, I have no idea. So we actually just wrote a transformation pass, which actually 2 days ago, I think, so it didn't make it into this slide deck. But essentially what it does is it pulls out the load, but the induction variable load and the buffer, and pulls it out of the loop header so it can be resolved because of some quirkiness with LLVM. It errs on the side of safety because that could be modified ahead of time. So.
Prove that this pass is actually safe and doesn't modify a program. Say if you have some nasty shotgun pass which shouldn't have really anything that aliases.
So this is not actually modifying like the actual execution of it. Well, I was talking about this before. So, if I understand correctly, so say like you have some sort of loop and the loop counter's modified internally. Is that what you're talking about?
No, the upper bound is being modified. Say if the loop itself modifies the buffer.
I think it's covered by alias analysis, the alias analysis pass, but I could be wrong. Okay. It's something we'd have to look into.
So you make sure there are no aliases.
Yeah, LLVM has a pass called alias analysis, and don't quote this is like gospel because I'm not sure, I haven't looked into it yet because we're still doing the analysis of this modification, but it's definitely worth noting. But in general, at least the induction variable is taken care of, and I can't speak to the upper bound, but I'm almost positive it's covered. So that being said, we could pull it out of the loop header, and it can be resolved later on as to whether or not it has an upper bound. So we'll classify that as TC, sub-TC rather. So in the next couple slides, I'm going to be discussing what we're seeing in the kernel in a large scale. And you have to bear with me because the information can get kind of complicated to describe, but here's an example of a contrived example. For example, if you had a folder structure on the, like I think you see on the right-hand side there, as such, and we want to represent the number of text files in this folder structure and their relative sizes, this would be a way to do it. So take, for example, the temp folder. It has a lot of files in there with, it has a lot of slock in that subfolder, but absolutely no text files. The server folder has a moderate slock to it and a lot of text files. So the saturation, the color saturation of the graph represents how strongly it correlates with the title of it. So just, I know that sounds complicated, but 9 out of 10 people in my office didn't understand this graph at first, so bear with me. So what are we seeing when it look at the kernel? So believe this or not, and this is a zoomed in view because it's just an untenable mess otherwise. We see a lot of terminating loops so far in the ARC-x86 folder, as well as you see a little bit of in the drivers folder as well as kernel and time, but a very high concentration in ARC. And you'll notice that at least no terminating, and you'll see in the next slide, no loops at all almost in the includes, which is not terribly surprising. But so as far as unbounded, and when I just say unbounded, I'm erring on the side of caution, so we don't know yet, we haven't determined. Same thing, we have a tremendous number of loops in ARC. You see a much more heavy weighting now to drivers, and also some of the scheduling and event handling in the kernel subfolders. But again, almost nothing in include Linux or the include folder at all. So just to talk about, get a feel for where we could be directing our efforts as if we had to do manual analysis on things, we just did a ratio of the unbounded versus termination. ARC seems to be a good candidate. I've looked at the drivers folders by hand, and they look like a fairly good candidate for classification for sub-Turing completeness as well. It should be noted, like I said, this is zoomed in, so you don't see folders like MM or anything like that, or FBDiv, but the same sort of trend follows around. So as far as raw numbers, what we've seen so far, and this is pending update, around 350,000 lines of code, 96% of which are ANSI, C. And I know that the undecided loops sound pretty high compared to the terminating, but when you look at functions with undecided versus the total number of functions we've seen so far, it's fairly small. So if you go back to this image here, half of this image is unlooped, basically. So what do we take away from this? Well, much of the Linux kernel already can be run sub-TC. Fantastic. So that's great that it means that it might be descriptive that a lot of the code that we normally write from day to day already can be a candidate for porting to a restricted environment for programming. It is possible, we've done some work on it already, to modify loops to make them more obvious as to whether or not they can run in a sub-TC manner, or whether or not they can't at all, and that's okay too. Additionally, it would be interesting, I think, for future work to apply this to other domains, so be it application servers or other client-side code, because I think you'd see a lot more variation in the types of loop you'd see, more recursive calls, just generally different types of programming styles there. Additionally, because the Linux kernel is so stable, monolithic, it's had a lot of chance for refinement. Whereas in the user code bases, you really don't have that luxury a lot of times. So if you're pushing out a user space product, you don't have the luxury of always cranking out the best code, just the one that gets the job done at the end of the day. And I think that would be an interesting way to look at those pieces of code base, those code bases, and do comparison. I'd like to thank DARPA and Tim Frazier for sponsoring this research effort, and Sergey Bratis for his technical support, pursuit of all things LangSec, et cetera. Any questions? Thoughts?